Howdy, howdy, folks. Welcome to Psych 63 Lab, Module 2, where we're going to be talking about orthogonal contrast, polynomial contrast, and moderated regression. So if you couldn't tell already, those are three kind of distinct subjects that we're going to be talking about. So I've separated this into three different parts. So first we're going to talk about orthogonal contrast, then we're going to talk about polynomial contrast, then we're going to talk about moderated regression. Now, given that, what I think the best way for you to do your assignment for this is if you do your assignment in parts as well. So I'm going to explain to you everything about orthogonal contrast, then I'm going to recommend you pausing this video, then doing part 1 of the assignment. Then I'm going to explain to you polynomial contrast, and then you should do part 2 of the assignment, and then I'll explain moderated regression, and then you'll do part 3 of the assignment. I think it'll be better if you do it that way rather than watching the entire video and then going back on the assignments. Just this time, we might have things like this in the future, but I think for this lecture it makes the most sense to do it that way. So let's go ahead and get started with part 1, orthogonal contrast. So I wanted to first kind of give you a quick review of what planned contrasts are in general. So remember, a contrast tests a specific hypothesis related to group means based upon some prior information about the groups. Additionally, contrasts assign a weight to each of the groups in your predictor variable. Some rules associated with these contrasts that the weights should always add up to 0. Additionally, assigning a weight of 0 means that that group will not be included in the contrast. You remember when you're adding those zeros and ones or halves or 0.5s or whatever. That's to determine what our groups that we're going to be comparing are. Additionally, the order of the weights correspond to the order of the groups in your predictor variable. So if you're corresponding to some independent variable and that has 3 groups, remember that it has to correspond exactly to what groups you want to do in R. So just an example of kind of a planned contrast here. We have contrast 1 here, which is testing whether or not the control group differs from the groups that received drug treatment in general. So we're saying, does control differ from the average of drug A and B? Additionally, contrast 2 here is saying, do the drugs differ from one another? We're not including the control group in here. All we're saying is, hey, is drug A different than drug B? Now, something to notice about these contrasts, as I stated previously, is that they sum up to 0. So -1 plus half equals 0. Additionally, 0 plus -1 plus 1 is equal to 0 as well. So that's one essential component to contrast, is that they sum up to 0. Now, orthogonal contrasts are contrasts, but with another layer added on top of them. So a set of contrasts is orthogonal if the number of contrasts is equal to the degrees of freedom. So if you have 3 groups, the number of orthogonal contrasts you can have is 2. If you have 4 groups, the number of orthogonal contrasts you can have is 3. Additionally, it's a requirement that you have at least 3 groups to compare. This doesn't work with 2 groups. There's not an orthogonal contrast if you only have 2 groups. Additionally, this is going to be a mouthful, but 2 contrasts are orthogonal if the pairwise products of the corresponding coefficients for each term sum to 0. And I'm going to go ahead and explain that to you right now. So let's take our previous thing. We're going to determine whether or not these are orthogonal or not. So we say, first of all, the number of contrasts is equal to the degrees of freedom. So we have 3 groups. So the degrees of freedom is 2. So we have 2 contrasts. Yes, okay, we're on track 1. We have at least 3 groups to compare. Yes, we have control group, drug A, and drug B. So we're good. Then we're saying 2 contrasts are orthogonal if the pairwise products of the corresponding coefficients for each term sum to 0. And what that means is, does the product between the pairwise comparison of each of them sum up to 0? So we take the product of -1 times 0 equals 0. Half times -1 is -0.5. Half times 1 is 0.5. And if we sum up the products of those, it'll sum up to 0 as well. So not only does it sum up to 0 when you go across a contrast, the products of the pairwise comparisons between of them also sums up to 0 as well. And that's the main components that make a contrast orthogonal. So we can use orthogonal contrast to get a lot of information about a data set, even if we don't have the full ANOVA table. And what we're going to be doing today is getting these orthogonal contrasts and calculating the sum of squares contrast. And from there, after we calculate the sum of squares contrast, we're going to get the effect sizes as well. So One of the main equations we're going to be working with today is this SS contrast equation, where N is the number of participants per cell. It's not the total N, it's the number of participants per cell. Additionally, we want to get the summation of the contrast times the mean squared over the summation of each of our contrasts squared. And I know that may not make much sense now, but in the later slide, I'm going to detail it and I'm going to map all the numbers so that you can actually do some plugging and chugging if you want to. So this is what we're going to be working with today. We are going to be working with 3 groups with mean scores of 35, 40, and 45. There was 90 participants total in the study and 30 participants per cell. So that means that 30 people were in group 1, 30 people were in group 2, and 30 people were in group 3. Now we want to set up these contrasts, and we can go ahead and check to see, are these contrasts orthogonal? So we say, okay, well, let's go through our 3 things. So is it equal to the number of groups minus 1? Yes, we have 3 groups and we have 2 contrasts. The group 1, group 2, and group 3, and we have 2 contrasts. Are there at least 3 groups? Yep, we're on the right track. Additionally, do those pairwise comparisons sum up to 0? So negative 1 times 1 is negative 1. Negative 1 times negative 1 is positive 1. 2 times 0 is 0. So negative 1 plus 1 is equivalent to 0. So yes, we are on track for having orthogonal contrasts. And additionally, something I want to know is that we gave you the SS total here, which is going to be 5,000, and that's going to come into play later. So let's look at what contrast 1 and contrast 2 are doing here. So contrast 1 is testing whether the mean of Y for treatment group 3 was significantly different than the means of the other 2 groups. So we're saying, is group 3 different than groups 1 and 2? Contrast 2, on the other hand, tests the hypothesis that the mean of group 1 was significantly different than the mean of group 2, it completely ignoring group 3. So we're saying, is group 1 different than group 2 in our contrast 2? So in this demo, I want to walk through how we're going to get the sum of squares contrast for contrast 1, as well as getting the effect size. And then for your assignment, I'm going to have you go ahead and just calculate contrast 2 by yourself. And I think I give you some information that'll make it a lot more clear too. So here's the slide that I was saying where I gave you the ability to just map these numbers onto the equation. So this is the equation that we're working with, and I give you the information necessary for that equation. So let's go ahead and run through it step by step. So the first thing in our equation is this N. That's the cell means. And if you remember from the previous slide, our cell mean was 30. So it's 30 times this sigma, this uppercase sigma means the sum of C is our contrast times the cell mean. That J there just represents, hey, I want the mean of a group. So our group 1 and group 2 and group 3. So what are we getting? It's the sum of the contrast times the mean of each group squared. So in this, the first thing we're going to do is do 35 times negative 1 plus 40 times negative 1 plus 45 times 2, and then you square all of that. Then divided by the summation of our contrast squared. So what that's saying is negative 1 squared plus negative 1 squared plus 2 squared. I know that it looks a little bit complicated at first, but once you kind of just look at it and see how these map onto everything, you'll be able to run your own contrast 2 as well. In fact, I'm going to let you in on a little secret. When you're running contrast 2, the only thing that's going to change are these contrasts, really, because the means remain the same for our orthogonal contrast. Anyways, so we go ahead, we add up, we do all the calculations. I kind of went through the steps here, and then we get an SS contrast 1 of 1,125. So what do we do with that 1,125? Well, we can calculate the eta squared, which gives us a wealth of information. So in order to get the eta squared of the contrast, it's the SS contrast over the SS total. So our SS total was given to us already. It was 5,000. It was 5,000. So we know what that is. So our eta squared for contrast 1 equals 1,125 divided by 5,000, which is equal to 0.225. So what we're saying is that our first set of contrasts is explaining 22.5% of the variance in y. That's explained by this contrast. And that's really the main thing. So what I'm going to have you do is do the same exact steps, but you're going to be doing it for contrast 2. And this is me just telling you where we got those numbers before so that there's not confusion in the slides for later. I have found this great article online if you want to read more on contrast as well and orthogonal contrast that you're welcome to read as well. So I have that available for you. Okay, so this is the part where I'm going to go ahead and suggest that you pause the video and you go ahead and try to do part 1 of the assignments, okay? And I'm going to go ahead and pause the video as well. All right, so let's get started on part 2, polynomial contrasts. So what are orthogonal polynomial contrasts, aka trend contrasts, and why do we even use them? So what they do is they allow us to evaluate nonlinear relationships between categorical predictors and a continuous outcome. So with continuous predictors, we can model these by just squaring the x to test the quadratic effect and cubing x to test the cubic effect essentially within your regression equation. But because we're working with categorical predictors, we need to use polynomial contrasts to test the different effects. And we're going to tell you what these polynomial contrasts are. They can be found online, or I supply them to you on slide 27. I supply you the polynomial contrasts available for linear trends, quadratic trends, cubic trends, and even quartic trends. So, and just a little advising, this type of coding system should only be used with an ordinal variable in which the levels are equally spaced. And I'm going to give you a data set in which the levels are equally spaced. But when you're thinking about your own research, you need to make sure that, make sure the conditions are equally spaced. You can't do like 1, 3, 4, 7, 8, or something like that. It has to be like something like 1, 4, 8, 12, or something along those lines. But with these effects, we can evaluate with more than 3 levels of a categorical predictor. If we have something with more than 3 levels of categories, we can assess a linear, a quadratic, and a cubic effect. And a linear trend is essentially saying as one thing increases, the other thing increases as well, and it's a constant linear trend. A quadratic trend says, yeah, things will increase for a certain dose until a certain times, then the trend changes, or vice versa, where it goes down and then up again. But it's saying, but essentially it's saying there's one bend within our curve within the quadratic. And then a cubic effect would be saying, yeah, there's 2 bends within our curve actually. It's saying something goes up, then it goes down, and then it goes back up depending on the dosage that you give it. And I supply you kind of the equations that are associated with this and how they look in a regression equation. So y equals a plus bx, that's simple algebra that you've learned before as well. Y for quadratic effects, y equals a plus bx plus bx squared. And then for a cubic effect, it's a plus bx squared plus bx cubed. So what we're going to do is I'm going to go ahead and I'm going to be switching off between the PowerPoint and the R notebooks to kind of explain some concepts while we're going through, because this kind of requires me to explain some concepts, okay? But the first thing we're going to do, actually before we even download the cogtest.csv, is we're going to go ahead and create a new R project. So I'm going to go to R, go ahead and create a new R project, go to new directory, new project, make sure that it's saved in the correct directory, and it is. And I'm going to name this module 2. I'm going to go ahead and create that project. There we go. Okay, I'm going to go ahead and go to our Canvas page, and I'm going to go ahead and download the data set. I guess I thought I had Canvas open, but apparently not, so let's go ahead and get it open. So CSU Canvas. Go ahead and log in. So the data set that we're going to be using for this is a cogtest.csv. So we scroll down to module 2 lab, and we're going to download the cogtest.csv. Go ahead and do this, download, open it up, do file, save as, browse. Okay, make sure it's a CSV. We'll go to our desktop, Site63, module 2. That's a new R project file that we just created. Save. I'm going to go ahead and exit out. And we can confirm that, yep, it did go ahead and create it. So let's go ahead and create a new R notebook. We're going to go ahead and delete all this unnecessary text. We're going to go ahead and name this, title this notebook Polynomial Contrast. And we're going to go ahead and set up our table of contents. Let's see, colon yes. And I'm going to go ahead and save this. I'm going to go ahead and name this module 2 notebook. I'm going to write polynomial because I think that we're going to go ahead and create 2 notebooks throughout this session because for the next section as well. So I'm going to name it polynomial. Go ahead and save. Okay, so let's go ahead and I'm going to be referring back and forth between the slideshow and the actual R code. And let's see what we have to do next. So we're going to be loading up 3 libraries today. It's a psych package, tidyverse package, and OLSRR package. And you should have these all available from last semester unless you got a new computer or something like that. So let's go ahead and do load libraries. So I can spell. Insert R. Okay, we're going to do library, psych, library, tidyverse, and library, OLSRR. Okay, we're going to go ahead and run that. There we go. I'm just going to run it again so we get rid of that output. There we go. Perfect. And let's see what we got to do next. Next thing we're going to do is we're going to download the data set, but I want to kind of explain what this data set is saying first. So really what's going on is researchers were interested in the effect of time spent in practice on the performance of a visual discrimination task. So subjects were randomly assigned to different levels of practice following which a test of visual discrimination was administered, and the number of correct responses were recorded for each subject. 40 subjects were randomly assigned to practice of 0 minutes, 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes, 12 minutes, or 14 minutes. Notice how those are equally spaced. That's going to be really important for what we're doing today. So there's 2 variables in this data set. There's the practice variable, which is just minutes spent practicing. That means they either found 0, 2, 4, 6, 8, 10, 12, or 14 minutes category. And then there's score, which is the outcome variable, which is the number of correct answers on the test. So we're going to go ahead and just read in that CSV file, okay? So we're going to do hashtag import data to insert R. So we're going to go ahead and name this cog. We're going to use an assignment operator to read underscore CSV. And with quotation marks, we're going to name it cog test.csv. Okay, so we do that. We should have a new object. Yep, we have a new object with 160 observations of 2 variables. So notice how there's practice of 0 and they have score associated with them. 4, 6, 8, 10, 12, and 14, and so forth. So all have score associated with it. There's no missing data. Okay, and we only have those 2 variables that we'll be working with. Now, let me go ahead and just see what we want to do next. Okay, so next what I want us to do is I wanted us to get some practice with the filtering function. It feels like it was a function that I taught you so long ago and we haven't utilized it very much, so I wanted to make sure we had some practice. What we're going to do is we're going to filter down our data set so make it so it's easier to work with. So we're going to make it so that we're only working with conditions 0, 4, 8, and 12. And I want to note that I kept those evenly spaced. So it goes from 0 to 4, 4 to 8, and 8 to 12, all in differences of 4 from each other. Like I said, I'm only doing this because I want to make it easier on us for when we're assessing linear, quadratic, and cubic effects. Okay, and I wanted to give you some practice with the filter as function as well. So let's go ahead and do filter our practice variable. Okay, so let me go and look at my notes here. Okay, so we're going to do insert a new R chunk. We're going to go ahead and we're just going to save this back into the cog data set. We're not going to worry about, we're just going to overwrite the cog data set. So I want you to notice right now it has 160 observations. We're going to be reducing that down using the filter function. So we're going to use the filter function, which is a function I feel like you haven't used for a long time. We're going to indicate the cog data set. And what we're going to be doing is making it so that we only get the practice sessions of 0, 4, 8, and 12. So only participants that fulfilled that condition. So what we do is we do practice is exactly equal to, so we use two equal signs, start off 0, then we do something called inserting pipe, and this is saying or part of this thing. And if you're having trouble finding that like little pipe symbol, it should be shift and it's the key right above enter where that slash is, okay? And then we do practice equals 4 is exactly equal to 4. And then we do a pipe saying or, so we want practice is equal to 0 or practice is equal to 4, or practice is exactly equal to 8, or practice is exactly equal to 12. Okay, so we kept those similar those spaces similar, and like I said, this is all just reducing the data set just so that it's easier for us to assess the effects. Go ahead and press play, and assuming we did it right, this number of 160 observations should drop down. Yep, so now we only have 80 observations. And if we look at our data set, before we had 0, 2, 4, 6, 8, 12. Now we only have 0, 4, 8, and 12, okay? And like I said, I just wanted to do that just to make it a little bit easier for a little bit later. So let's go ahead and go back to PowerPoint and see what the next thing we are to do. Okay, the next thing that we're going to do is we're going to go ahead and visualize the data, okay? So I'm going to go ahead and do a new header called visualize the data. Okay, so what we always use for visualizing data is our ggplot. So ggplot, remember, first thing we indicate is our data set, which is the cog data set, comma, then we set our aesthetic. And for this, what we're going to be doing is actually creating a geom point with a geom smooth layer under it. It's really cool. Geom point and geom smooth go really well together. So it's essentially a scatter plot with a regression line placed under it. So in order to get this, we're going to need an X and a Y aesthetic map to it. So we're going to say X is equal to practice, comma, and our outcome variable is Y is equal to score. Then we do plus, we're going to do a geom point layer, which is essentially a scatter plot, plus we're going to do geom underscore smooth, and this is going to set a regression line under our geom points. And what we do is we're going to set method equals quote LOESS, and that essentially is just saying that we want the line to be able to move freely, okay? With that method equals LOS saying we want it to be able to bend and curve so that it conforms to the data rather than being a straight line is what we'll be looking at today. So we go and press play there, and there you go. Don't worry about all this. This is just telling us some information, but we get a really neat looking graph. So as we can see, as practice goes up, it seems like the score generally goes up. But what we're going to be asking ourselves today is saying, does it go up in a linear trend, or does it go up in a quadratic trend, or does it go up in a cubic trend? Saying, how many bends are there to this curve, essentially, is what we're going to be assessing today. And we assess that through polynomial contrast because we have a categorical variable that we're working with. If we were working with continuous variable, we would just set it up in our regression equation, and we'll learn how to do that later. But for categorical variables, we need to set up these polynomial contrasts. Okay, but yeah, as we can see, it seems like generally as practice increases, so it goes from 0 to 4 to 8 to 12, there's an increase. But is it a linear trend? But is what we're going to be assessing. So let's go ahead and go back to the slideshow and see what we have next. Okay, so this table, we don't use every single piece of this table, but what this table is essentially telling us is what are the degrees of polynomials and what are some orthogonal contrasts that are associated with the polynomials that we'll be doing. So we have 4 treatment levels with our group. We have 0, 4, 8, and 12. Those are our 4 treatment levels. And so what we can do is we can assess 3 different degrees of the polynomial with 4 treatment levels. We can test a linear trend, we can test a quadratic trend, and we can test a cubic trend. We can't assess a quartic trend with our data because we only have 4 treatment levels. If we kept all of our data, then maybe we could have. But again, I wanted to make it simple on you guys. So what we're doing here is we're going to be assessing what are the correct trends, polynomial contrast that we're going to be setting to our data. And so what we do is we set up for a linear contrast, which is given to us here. And again, I didn't create these. These are something that someone else created for us. Is we're going to be setting it up for a linear contrast, a quadratic contrast, and a cubic contrast. If we had 5 treatment levels, we would be using this thing down here. If we had 3 treatment levels, we'd be using it right here. So really, where you use on this table is dependent on the number of treatment levels here. And as you can see, it has, as we look at the table, it has number of treatment levels. So there's 2, 3, 4, 5, and 6. We're going to be working with the 4s for this lesson. The degree of polynomials is saying, okay, 1, is there only one is this a linear trend for 1? 2 is saying, is it a quadratic trend? And 3 is saying, is it a cubic trend? And we'll be using these numbers to assess whether or not these are linear, quadratic, or a cubic trend. Okay, so the way that we do that is we're going to be creating new variables. We're going to be creating a variable called linear. We're going to be creating a variable called quadratic. And we're going to be creating a variable called cubic, in which case we assign that when these variables are equal, when practice is equal to 0, we set it to a -3. When a practice is equal to 4, we set it to -1 for a linear trend. When practice is equal to 8, we set it to 1. And that all this comes from the previous slide here, -3, -1, +1, and +3. These are orthogonal polynomial contrasts. So to do this, we're going to be using something called an if-else function. And we use it within our mutate function. And I give you a little hint here as to what the if-else function is, but I think it's going to be explained the best if I just go ahead and start typing it in and then show you kind of step by step what's going on. But essentially, the way that this if-else function works is we set up something called, use the if-else function, you set up what's called a test expression in which you say whatever a certain variable is equal to something or greater than or less than, here we're saying is exactly equal to 0, then you turn it into a -3, else it turns into an NA variable, NA value. So like I said, I think the best way to kind of teach you this is to just go ahead and start coding, and I'll do it step by step, explaining what's going on. Okay, so we're going to do hashtag mutate the variables for trend contrast. Let's say that. Okay, so remember, these numbers aren't coming out of nowhere that we're using. Numbers come from this table up here. That's what we're going to be doing. When we have 4 treatment levels, we're going to be using these numbers to get our orthogonal polynomial contrast. So what we do first is we're going to be rewriting over our data set. So we're going to be rewriting over the cog data set, and we're going to be using the mutate function to do that. Mutate, there, we indicate our data set cog. I'm going to go ahead and press enter a couple of times. And then I'm actually going to leave this down here. What we do is we're going to create a new variable called linear. We say linear equals. Then we use this if-else function, saying if-else, if practice is exactly equal to 0, so we use practice equals 0, comma, then turn linear, which is the new variable we're created, to -3. Else, make it an NA. Okay, so I'm going to go ahead and run this just to show you what's going to happen. We're going to start off simple and then we're going to build it up. So we have this cog data set. If you look here, it currently has 2 variables. When we run this, it's going to have 3 variables now. And we created a new variable called linear, where every time practice is equal to 0, it turns to -3. And it said else, keep it as an NA. And we're going to be building up on this so that whenever practice is equal to 4, it's going to be set to something else, to a -1 actually, for this linear. So first we're going to be building a variable called linear, then we're going to be building a variable called quadratic, then we're going to be building another variable called cubic, in which case we're testing these polynomial contrasts associated with it. Remember, these are orthogonal contrasts, so the cross products of them add up to 0. And that's what's so important about this. So we go ahead and do that. I'm going to do a comma, and I'm going to say linear equals if else, if practice is exactly equal to 4 now, comma, set it to a -1, else keep it as it was in linear, is what we'll be saying here. So, and just to be clear, that -1 came from here. So we had -3, -1, then we're going to be testing a +1, and then a +3. For treatment 1 gets -3, treatment 2 gets -1, treatment 3 gets +1, and treatment 4 gets a +3. So now what we're saying is, okay, I also want you to go ahead and rewrite over that linear variable and use this if-else function so that when practice is exactly equal to 4, I want you to set it so that it's a -1. Else, I want you to keep it so that it's the same as it was before. So let's go ahead and run this now. We're not going to have any change in the number of variables, but now when we look at our data set, okay, whenever practice is equal to 0, our linear is -3. And whenever practice is equal to 4, our linear is -1. We still haven't done anything with 8 or 12. That's what we're going to be doing next. So now I use a comma to indicate that I'm doing a new line. I say linear equals if else, if practice is exactly equal to 8, comma, I want you to change this to a 1. Else, keep it as linear. And again, that 1 came from here. So now we're using a +1 for our treatment 3. Comma, and I'm going to go ahead and just build off the next one here. Not linear equals if else. There's quicker ways you can do this, but I think that they're a little bit too advanced for this class, and I think that I'd rather just do it the long way. Do this. 12, then it's equal to 3, comma, linear. Okay, so if we run this entire set of code, we don't get any, let's see what I did wrong here. There we go, misspelled if else. There we go. Okay, now we're back on track. There we go, and it ran okay. So now, whenever practice is equal to 0, linear is -3. Whenever practice is equal to 4, linear is -1. Whenever practice is 8, linear is 1. And whenever practice is equal to 12, it's 3. So again, this is our first treatment, the 0s. This is our second treatment, the 4s. Our third treatment is the 8s. And the fourth treatment is the 12s. Okay? Now we want to start building it up so that we have a quadratic variable. So our quadratic, for treatment 1, it's going to be +1. For treatment 2, it's going to be -1. For treatment 3, it's also going to be -1. And for treatment 4, it's going to be +1. So we want to build that up in our contrast statements here. So I'm going to go ahead and leave a couple of lines here. Now I'm going to be creating a new variable within the mutate function called quadratic equals if else. And it's going to be practice is exactly equal to 0, comma, and it's going to be a 1. Else it's going to be an NA. And we use that NA because we need to initialize some sort of variable here. We can't leave it blank. So that's why I use that NA. So if we go ahead and run that, you're going to see another variable get built up here. It has 4 variables now. Now we're building up another variable called quadratic, in which practice is equal to 0, it's 1, and then we're going to be using these values here to build up what the quadratic one is. So let's go ahead and just go ahead and do it. So else, so comma, quadratic equals, overwriting the quadratic variable, practice equals 4, comma, going to be -1, comma, keep it else, keep it as quadratic, comma, quadratic equals if else, practice equals 8. And I'm going to go ahead and look up here real quick. There we go, comma, and turn it into a -1, else keep it as quadratic. Then we're going to do one more time, quadratic equals if else, practice equals 12, comma, then this turns into a 1, comma, else keep it as quadratic. And again, I want to just remind you again that these numbers aren't coming out of thin air. They're coming from this table here. 1, -1, -1, +1. Treatment 1, treatment 2, treatment 3, treatment 4. Okay, so I'm going to go ahead and run that and make sure things are running appropriately. They are. And now we have this new variable called quadratic words. When it's 0, it's equal to 1. 4 is -1. When practice is equal to 8, it's still -1. And when practice is 12, it's 1. And we have that throughout the entire data set. Now we're going to build up for our cubic trend to test for. And you'll see what we're using these kind of variables that we're creating for later when we're going to be running actual regression analyses with them. So now we're going to create a new variable called cubic, which is going to equal if else. If practice is exactly equal to 0, comma, n is going to be -1. Else, set it to NA. We're just initializing that variable. And I'll go ahead and press play real quick. We have 5 variables now. So now whenever practice is 0, cubic is -1. Then we do comma, keep it all in there, comma, cubic equals if else, practice equals 4, comma, going to be 3, else it remains cubic, comma, cubic equals if else, practice is exactly equal to 8, comma, it's going to be -3, else it stays as cubic, comma, and this is going to be our last one, and then we're done with this, this coding here. Cubic equals if else, practice equals 12, comma, 1, else it remains cubic. Okay, so I think it's all done there. I'm going to go ahead and just delete this line. Okay, so that's a lot in one set of code. And it shows the power of mutate. We can create 3 new variables with just one mutate function. And just to show you one more time, I hope I'm not getting too annoying but this cubic, the way I got those numbers is from here. Treatment 1 is -1, treatment 2 is +3, treatment 3 is -3, and treatment 4 is +1. So if we go ahead and press play, we should have, yep, it's completely filled out. So now you're probably asking yourselves, well, Neil, what do we do with this? Okay, we spent all this time creating this. What do we do with this? Well, we're going to be testing if this practice variable is appropriate for a linear effect or a quadratic effect or a cubic effect. We're going to be testing with a regression equation. So the way that we do that is we plug in these new variables that we created one at a time to test whether there's a linear effect. Then we're going to plug in a quadratic variable, see if there's a quadratic effect. Then we're going to plug in the cubic variable, see if there's a cubic effect, okay? So let's go ahead and do that. So let's go ahead and, let me just look at my slides here. Let's go ahead and say hashtag plug in the newly created polynomial contrast into a regression equation. And that's what we'll be doing. So do hashtag first start with linear, insert a new R chunk. So I'm going to try and keep with consistency on this. I know it's kind of weird that I start with M3. I got these from an old slide and I didn't change the numbers, but we're going to call this M3. We're going to call this model M3. And that is going to be the LM, the linear regression of score, which is our outcome variable, regressed on. So it's going to be score. Our outcome variable is score, regressed on linear. These newly created polynomial orthogonal contrasts that we created. Linear, comma, theta equals cog. Then we're going to do OLS underscore regress M3. So we're creating a new model called M3, which is just score regress on that linear variable we created here, and then we're going to just get the output of that. So it looks like it is. All right, good. We're in business. So the R squared value is 90.909. So remember, that's 90% of the variance is being explained by this linear variable alone. That's a lot of variance being explained. So it's saying that there's a potentially, we're going to look at the actual significant effect here soon, but that's a lot of variance to be explained by some sort of linear effect. So what we're saying is, we go back up here and say, yeah, there is somewhat of a linear effect associated with this that we're looking at. And we'll just confirm, yes, I kind of went ahead, but yes, there is. So what we're saying is, we don't really look at the numbers. What we're mostly focusing on is the significance here, is saying, okay, yeah, it's got a slope of 3.523, and that's a significant trend. So it's saying, yes, we have a linear trend, okay? Now, we're going to go ahead and test, say, is there a quadratic trend associated with this practice variable on score? So, let's go ahead and do hashtag second test the quadratic trend. So, we'll go ahead and I'm just going to go ahead and actually just kind of copy and paste this actually, and we're going to make a few changes to it. So we're going to change this to M4. All we're going to do is add our quadratic variable. And we're going to say, hey, okay, we know there's a linear trend. Is there also a quadratic trend? So we go ahead and check that. So all we do is we're going to regress our score on our linear plus our quadratic trend. So here we go. And so our R squared jumped up to 0.98. 98% of the variance is being explained by our model, which is assessing the linear and the quadratic trend. Okay, so we have a significant model. And what we're saying is, okay, yeah, there is a significant effect here. Saying, yeah, there's a quadratic trend associated with this. So it's saying this line has at least one bend associated with it. Saying, yeah, it's not a completely straight linear trend. It's saying that there's a bend to it. So we can go ahead and assess that there's a bend associated with this. Next, what we're going to do is we're going to test to see if there's a cubic trend associated with it. So again, I'm just going to go ahead and copy and paste this because we're only going to be making a few changes. We're going to do hashtag third, assess if there is a cubic trend associated with. Let's just say it's assess if there's a cubic trend. And then we're going to go ahead and insert a new R chunk. Delete this. And the only difference that's going to be changed in our model is we're going to rename our models to M5 plus cubic. So now with that newly created polynomial contrast that we have created up here, we're going to say, is there a cubic effect associated with it? So I'm going to go ahead and play that. And we're going to let our OLS regress. It looks like, okay, well, before it was 98% and didn't really change too much. So we're kind of questioning at this point while we're waiting for it to load, like, was there really any change with the addition of the cubic effect? And what I can tell you is that no, there's not a cubic effect associated with this. When we're looking at our significance is 0.475. And we're saying, okay, yeah, it doesn't look like there's a cubic effect. So it looks like there's only one bend associated with it. So our best model to go with is this quadratic effect, in which we say, yeah, there's one real bend associated with this. It seems like it kind of curves up like this is the main thing associated with it. So that is, let me go to the slides. Okay, and on the slides, I give you more information as well, in which I'm saying, well, we're assessing for the linear effect, then I'm saying we're assessing for the quadratic effect, then I'm saying that we're assessing for the cubic effect, and there's no evidence to suggest that the cubic effect is. Now, I want to go back up to here, because you're not always going to have 4 treatment levels when you're doing this. You might have 2 treatment levels. So if you had 3 treatment levels, let's say, these are the numbers that you would be working with. You can only have 2 degrees of polynomial. If you have 3 treatment levels, you can only assess a linear trend and a quadratic trend. You can't assess a cubic trend. If you have 5 treatment levels, these are the numbers you'd be associated with here. It's essentially what you'll be doing is exactly what we did up here, but you'll be filling in the correct numbers. So make sure you that's something that's important to keep in mind, that these numbers correspond correctly to the numbers on this table. Okay, so I have some more information too. If this was confusing, I have some other ways. I think it's great to have other ways of people explaining it as well. I gave you a couple more resources on the categorical variable coding system with polynomial contrast as well. So this is the point now where I'd say, hey, let's go ahead and pause the video and see if you can work on part 2 of the assignment, okay? And I'm going to go ahead and pause the video as well. All right, students, let's go ahead and get started with part 3, which is moderated regression. So what is moderated regression? Well, we have this thing that's called a moderator variable, and a moderator is a variable that changes the relationship between two or more, honestly, other variables. So moderation models are used to determine the magnitude and or the direction of a certain regression slope varies as a function of some third variable. So before we were always talking about the relationship between x and y. In moderation, what happens is that there's a z variable that's changing the relationship between x and y. It's saying for every 1 unit increase in z, there's a change in x on its effect on y. So our interaction term is the predicted difference in the effect of x on y for a 1 unit increase in z. So as I stated earlier, as z increases, it affects how x is on its effect on y. So there's this third variable that's playing a role, and what it's saying essentially is that as z increases, the slope of x changes. So the slope isn't exactly the same. The only way that you can determine the slope of x is if you know something about the where z is. So we can also visualize our interactions as well. So as we can see here, this is what it looks like when there's no interaction observed. Essentially, the lines are parallel with each other, okay? That's an indication that there's not a interaction involved. However, if the slopes are different on a counter of z, then we're saying, okay, there's some sort of interaction involved. Either the slopes are going away from each other or they're going towards each other and they're going across, is what it would be an indication of an interaction. So it's really nice to visualize these interactions, and I'm going to show you a visualization later as well. So let's go ahead and dive right into R, okay? So we're going to go ahead and create a new notebook that's separate from your polynomial notebook that you created earlier. So you go to your Psych63 Module 2 folder, and you double click on the project file, and it'll open up a new R project folder for you, or a new R notebook for you. And what we're going to do is we're going to go ahead and download the data set here. For this one, we'll go to Module 2 Lab. We're going to download the moderation demo.csv folder data set. Go ahead and download that. And we're going to do File, Save As, Browse. Go ahead and save it go to the correct folder. There we go, save it. Perfect. Okay, and then let me just go ahead and go. I'm going to be switching off between the R notebook and the slideshow most of the time. So let's go ahead and create a new R notebook. I'm going to go and delete this unnecessary text. Go ahead and name this moderated regression. And we'll go ahead and create the table of contents. EOC:yes. And we can go and save this as well. I'm going to go ahead and name this module _2 notebook. And I'm going to name it moderation, so that we can keep it distinct and different from our polynomial notebook that we created earlier. Okay, so the first thing we're going to do is actually, I'm going to load up some notes for myself. All right, the first thing that we're going to do is we're going to load our libraries. So we're going to be using the Psych library, the Tidyverse, and the OLSRR packages today. Do hashtag load libraries. Do insert R. So we do library, Psych, library, Tidyverse, and then library, OLSRR. So we'll go ahead and play that. Okay, looks like it all loaded up successfully. Go ahead and press play again. Go back to our slideshow and see what our next step is. And we're going to go ahead and reading in the CSV file. So we'll do hashtag import data, insert a new R chunk. We're just going to name this dat. We're going to use our assignment operator, use the read underscore CSV function, and it's going to be moderation underscore demo dot CSV. Go ahead and press play. Here we go. So we have 692 observations of 11 variables, and it's good that we have a big data set because if we're going to be running interactions, we need large data sets to detect certain interactions. Power is extremely important when we're running interactions, so a big data set is kind of essential to this. Okay, so we'll go into the next slide, and then what are we going to do next? Next, we're going to go ahead and describe the data set. So we'll go ahead and do describe data. Insert an R chunk, and remember from the psych package describe and then the data set that you're working with, describe dat. Okay, so this is our data set, and I have it available here too. So we can get a few things. So I just want to note, this is just a simulated data set. The variables don't have any real specific meaning, but as we can see, we have these kind of 5 variables called at 1 through 5. There's group 1 and 2 that we're not going to be working with at all, and then out 1 through 4. And essentially, it seems like on average, the mean value is about 1, a little over 1, sometimes 2, depending on what you're looking at. And the minimum, it goes from 0 to 9 for our at variables, and our outcome variables, it goes from 0 to 9 as well. Okay? So today, we're going to be working with 3 specific variables. And you know what? I think I'm going to actually make it so that we reduce the data set as well, which isn't in the PowerPoint slideshow, but let's go ahead and reduce the data set, okay? So let's go ahead and do hashtag reduce data set to variables of interest. And if you remember how we did that before, we used the select statement from the tidyverse. So we'll go ahead and just rewrite over the dat. We're going to do select. We'll do dat, comma, and then we're going to keep the at 1, comma, at 3, and out 4 variable. It's the only variables that we're going to be working with today. There we go. All right, it's a nice clean data set that we're looking at. They're much smaller. I don't have that in the slideshow, but I figured that it's a better way to go actually. So as you can see, we're only going to be working with the at 1, at 3, and out 4 data sets. Remember, this is a simulated data set, so they don't exactly have meanings to them. And the next thing we're going to do is be creating a cross product. And this is going to come in handy later when we're actually running the interaction. So we're going to do hashtag create the cross product of at 1 and at 3. Insert R. So how we do that is we're going to be using the mutate function. So I'm going to do dat, our assignment operators, and then we're going to use mutate. And we'll indicate the data set again, which is dat. And then we're going to name a new variable. It's going to be called at 1, at 3 equals. And it's just going to be the product of at 1 and at 3. I'll explain how, and we'll see how we're using this later on. So now we have a new data set with 4 variables, which is at 1 and at 3. And as you can see, and I think I have it in the slideshows here too, it's really just the product of at 1 and at 3. 3 times 1 is 3, 0 times 0 is 0, 3 times 2 is 6, 0 times 1 is 0, and so on and so on. So we created a new variable called at 1 and at 3. That's going to be our interaction term that we're going to add into our model later. But first, we're going to build a main effects model. So let's go ahead and create a new header for ourselves, and we're going to do run moderated regression, and we're going to be pretty specific with this title, in which at 1, at 3, and at 1 times at 3 predict out 4. And then we're going to say step 1, build main effects model. And we're going to be using this because we're going to have to compare our model later. But we're going to build this main effects model first just to look at it. And I think it's good because I think we're going to get a good refresher on what regression is with just building the main effects model. So let's go ahead and name this model mod ME for model main effects. And then we'll use the LM function. We're going to do out4, which is our outcome variable, regress on at1 plus at3, comma, data equals stat. Then we're going to go ahead and use the OLS regress function to output our mod ME. So we go ahead and play that. We have a new list of 12 for our new object for our mod ME. We're explaining 20.6% of the variance with our model. 20.6 of the variance in out4, I should say. And I'm going to go ahead and do a quick refresher on how we interpret these regression models. So remember, you start up here, you look at your R-squared model, and it's explaining 20.6%. We look over here and say, okay, is this a significant model? Yes, it is. Then we go down to our intercepting coefficients, and we can view these. So remember, the intercept specifically is what our outcome variable is when at1 and at3 are at 0. So when at1 and at3 are 0, our expected value of out4 is 0.655, and that's significant. Then we can look at at1 and say, for every 1 unit increase in at1, there's a 0.049 increase in out4. And essentially, that's not significant. And then lastly, for at3, we can say for every 1 unit increase in at3, there's a 0.458 increase in out4, and that is significant because our significance level is less than 0.05. Okay, so now that we got a good refresher on our main effects model, we're going to go ahead and run the interaction model now. So we're going to do hashtag, or it'll be a double hashtag. Hashtag step 2, run the interaction model. And all this interaction model is just the same model that we ran before, but we're adding in that at1, at3 variable that we created earlier. Okay, so we're going to go ahead and we'll name this mod int for mod interaction, and we'll do lm. We're going to do out4 regressed on at1 plus at3 plus the cross product of at1 and at3, 3, comma, data equals that. Then we'll do OLS underscore regress mod int. Okay, so we go ahead and play that, and it'll load up. Okay, so we're explaining 0.213 of the variance, 21.3% of the variance in out4. It's a significant model. And then we're almost done loading it up. Perfect. So we have our intercept of 0.757. Now these are considered simple slopes now because of the interaction that's associated with it now. So at1 and at3 are now simple slopes. And I have a good description of what these actually are in our slideshow here. So what I'm saying is models of results with the interaction term. These take on a new form, this at1 and at3. These are now simple slopes, and this is the interaction between the two. So what we're saying with these simple slopes now, and I'm going to go ahead and explain it one by one. So to start off with our at1, what this is in the presence of an interaction term, and our interaction term is the at1, at3. In the presence of an interaction term, at1 means it is the predicted change in our outcome variable for every 1 unit increase in at1, specifically when at3 is 0. So it's when the other variable is 0. Additionally, at3 is the predicted change in our outcome variable for every 1 unit increase in at3 when at1 is 0. Now, the big change is the at1 and at3. So what this is, it's the predicted change in the effect of at1 on our outcome for every 1 unit increase in at3. Okay, so as as at 3 changes, the slope of at 1 changes as well. That's what we're saying. It's saying that whenever at 3 changes, whenever at 3 increases, the slope of at 1 changes as well. So what we do is we can simply add up, we can do for every 1 unit increase, whenever there's a 1 unit increase in at 3, we add 0.49 to at 1, and that's the new slope that's associated with it. So the slope is changing based on what our effective at 3 is. And we'll be able to view this a little bit later. But first, what I want to do is we're going to run a hierarchical regression to compare the main effect model to the interaction model and say, is there a significant difference between the two? So if you'll recall, we learned about hierarchical regression in Psych 652. So what we're going to do is use compare the two models using hierarchical regression. Okay. So we go and insert a new arc chunk. And remember, hierarchical regression is actually quite easy. All you have to do is just type in ANOVA and the models that you want to compare. Now remember, these models, there are only one thing that's different between them. It's the addition of the interaction term between the main effects model and the interaction model. So we'll go ahead and do, first we enter in the smaller model, which is the mod ME, comma, and we put in the larger model, which is the mod interaction, which is the addition of that interaction term. And we press play, and we're simply going to be asking, is there a difference between these two models? And the answer is yes. There's a significant difference between our two models. When we add in the interaction term, there's a difference between it. It's explaining more variance. So it's saying, yeah, this interaction term is justified to be added in there. Okay? Now, and this is where I just explained to you how the moderated regression model explains significantly more variance in at 4 than the main effects model. So this is what's going on. Whenever at 1 is changing, so is at 3. And it changes on this. So as you can see here, when the lines cross, the slopes are also different as well. So as at 1 changes, so does at 3. So they're dependent on each other essentially. As one increases, the other one increases as well. It could be a decrease, but in this case, we had an increase. And if you want, I'm not going to run it in R, but you could go ahead and you can copy down this code. Make sure you install the sjplot and sjmiss packages, but you could plot your own model as well. I gave you the code to do that. But what I want you to focus on is that there's differences in the slopes of the lines based on one variable, okay? The lines cross and the slopes differ here. And I wanted to just show you that there's also an alternative way. Instead of creating the cross product for the interaction term as we did before, you can go ahead and you can just create the cross product within the regression equation. So essentially just doing at 1 plus at 3 plus at 1 times at 3 is the same thing as doing the cross product. I just wanted to make that clear that there's two ways of running these interactions as well. And this is an example APA write-up. So the differential effect of at 1 on at 4 using at 3 as a moderator was examined among 692 participants. A moderation model was estimated. So at 4 was regressed on at 1, at 3, and the interaction between the two. The simple slope of at 1 was not statistically significant, and the simple slope of at 3 was statistically significant. Those don't really quite matter as much, though. What we're really focused on is the interaction term. So the interaction term is statistically significant, indicating that the effect of at 1 on at 4 is larger as at 3 increases. So again, as at 3 increases, the effect of at 1 becomes more. So that slope is changing because of at 3. So I just wanted to end this off with some additional considerations with moderation. To start off, as I stated before, power is extremely important. The n needed to detect an interaction effect can be up to 9 times larger than detecting main effects. So for every interaction term you add, the n needed to detect the effect increases as well. There's also such things as three-way interactions. We're not going to go over them in this class. They're a little bit too complex, but it is very much possible. And additionally, interpretation is usually easier with categorical predictors. And if you want to, you can turn your continuous variables into categoricals by using cutoff scores. That's essentially what I did here, is we turned it into categoricals saying, when at 1 is 1 standard deviation below, when it's at the mean, and it's 1 standard deviation above. Essentially just saying that there's a difference in the slopes based on at 1 when we do that. And that just about sums it up. That's all I have for you today. Thank you so much for listening. Go ahead and start part 3 of the assignment. And please let me know if you have any questions through emails or during lab time. Thank you so much.